Hopefully we'll get some good work done here. Okay. So let me get the pen out. Here it is. Okay. So we have two events, A and B. If probability of A equals 0.43, probability of B is 0.26, and A or B equals 0.68. Now they're asking you, are they mutually exclusive or independent? Those are the two issues that are coming up. Okay? Well, what do you know? You know that the probability of A or B, they tell you what that is. It's going to equal the probability of A. Sorry. Probability of A plus the probability of B minus the probability of A and B. And this is the general addition rule, and this will be on your cheat sheet, A and B. Okay, so here's what you know. You know that A or B is 0.68. Okay? Probability of A is 0.43, and the probability of B is 0.26. So what is the probability of A? So these two numbers added together is 0.69. So the probability of A and B must be 0.01. You guys follow that? Okay. So we have an overlap of 0.01 between A and B. So they are not mutually exclusive. They have an overlap. Okay? Yes?
So where'd you get the 0.01?
The 0.01, we're told A or B. It's 0.6. First of all, I know that A or B equals probability of A plus the probability of B minus the probability of A and B.
Yeah.
Right? We're told probability of A or B. We're told the probability of A. We're told the probability of B. Probability of A and B adds up to 0.69. So we have 0.68 equals 0.69 minus 0.01. Right? Right? Okay, so A and B.
I'm just not seeing how you get 0.01 from it. Probability.
What's the difference between 0.69 and 0.68?
0.01.
That's what probability of A and B's got to be. Look, A is 0.43. All right. A is 0.43, right? B is 0.26.
Yeah.
A or B is 0.68. The formula A or B equals point A plus point B minus A or B, minus A and B. So if A and B equals 0.69, then the probability of A plus the probability of B equals 0.69. And A or B, we're told, is 0.68. Then A and B has to be 0.01.
Okay.
Okay? All right, so there's no overlap. If they're mutually exclusive, there's no overlap. Okay? So in other words, if they're mutually exclusive, the probability of A and B is 0. Okay. So we know that they're not mutually exclusive. Okay, so we can eliminate any answer that says that they are mutually exclusive. What about being independent? Okay? A and B are independent if the probability of A equals the probability of A given B. And the probability of A given B equals the probability of A and B. A equals the probability of A and B divided by the probability of B. Okay? Now the probability of A and B is 0.01. What's the probability of B? 0.43. And what's the probability of A? I'm sorry? I'm sorry, 0.26, right. Anyway, the point is 0.01 over 0.26 is not equal to 0.43. Okay? You don't have to use your calculator to figure that out. So they're not independent. So they're not independent and they're not mutually exclusive. So the answer is D. Yeah?
Can you explain independent and one more time?
Independence. Probability of A equals probability of A given that B has already occurred. That's it. And then the probability of A given B equals the probability of A and B divided by the probability of B. That's it. Okay? Now, you're not given this formula in the cheat sheet for independence. You've got to know it. Okay. Now, let's look at number 2. You guys already finished with 1? Okay. Number 2. Okay, each t-shirt, you got the expected number of t-shirts. Okay, school source sells monthly as the following probability distribution. Okay. Now, it goes 0 through 10. So this is X, the random variable X is the expected number of t-shirts shown. Okay, it's a discrete random variable because you sell t-shirts one at a time. Okay, each t-shirt sells for $10 but costs the store $4 to purchase. What is the expected monthly t-shirt profit? Okay, well, in order to do this, we got to find the expected number of t-shirts per month. Okay, so we take the calculator and we're going to put these numbers in. Now, I already put I'm going to load the numbers. So the numbers are in. I'm going to put in 0 through 10 in L1. That's the expected outcomes, number of t-shirts. And then in L2 are the probabilities. So put those in. And then I'm going to do stat and calc and one variable stats on L1 and L2. Okay, so the expected number of t-shirts sold is 3.78. Okay? So I'll give you a chance to catch up with me there. All right. Now, you're going to take that and you're going to multiply the expected number of t-shirts sold is 3.78. So we'll take 3.78 times the profit per t-shirt, which is 6. And you get $22.68. Okay? Yes.
The 6 is from subtracting 10.
Okay? Any questions? So the expected profit per t-shirt is $6. You sell them for 10 and you buy them for 4. And on average, you're going to sell $3.78 per month. Okay? Clear? All right. Number 3. Okay. Ambitious young woman's working 2 jobs and receiving tips. Hairdresser, her tips have a approximately normal distribution, $65, standard deviation of 575. Her tips for a waitress, $154 a week, and standard deviation of 802. What are the mean and standard deviation? So these are 2 continuous random variables. So we're going to do the expected outcome from the tips from the hairdresser plus the waitress, H plus W, and that's going to equal 65 plus 154, okay? And that's 219. All right, now, the standard deviation for capital H plus capital W is going to equal the square root of the 2 variances from each one. So 5.75 squared plus 8.02 squared. And that number is 987. So the answer is D. Okay. Okay? Continuous random variables, as long as they're independent of each other, okay, you can do this computation. All right. 13. Which of the following is not a condition for a geometric setting? A geometric probability is Bernoulli. So, one of the requirements for a Bernoulli is that there are only two outcomes. So A is required. B, a Bernoulli requires that the probability of success for each trial is fixed. Okay, so B is required. Bernoulli trials require that each trial is independent, so C is required. D, there are a fixed number of observations. That is not required. In fact, in a geometric trial, you could theoretically have an infinite number of trials. Okay? So, the probability is quite low, whatever. The variability of interest is the number of trials required to reach the first success. That is the definition of a geometric probability. Okay, so the answer is D, is the one that's not required. All the others are. Okay. Now, 5. Any questions? No? Okay, 5. Okay, you got a game of chance. Okay, 3 fair coins are tossed simultaneously. If all 3 coins show heads, then you win $15. If you get 3 tails, then you win 10. If it costs $5 to play the game, what's the expected net gain or loss after 2 games? Well, we got to figure it out for 1 game. All right, so we'll just call this G. All right, or no, let's call it. Yeah, let's call it G. Okay, so we got G, and then the probability of G. Let's call this winnings. Whatever. Let's stick with G. Whatever. Okay. So you can win 15, but it costs 5, so that's a net of 10, and the probability of that is 1/8. You can win 10, but it costs 5, so you can win $5, and the probability of that is 1/8. 3 tails. Or you can win nothing, having paid $5, which is -5, and the probability for that is 6/8 or 3/4. Yeah. 3. You're throwing three coins. Okay. So to get 3 heads, it's 1/2 times 1/2 times 1/2. 3 tails, 1/2 times 1/2 times 1/2. Okay. And so those are the only 2 outcomes in which you win money. In all other outcomes, all other combinations, you lose $5. Okay? So we go to the calculator to get our mean and standard deviation. So we'll go to Stat and Edit. And, okay. So I'm going to go up here and hit clear and enter. Okay, so we're going to put in 10, 5, and -5. Don't put in 0. Otherwise, you'll get the wrong answer, but it's one of the answers that's listed. 1/8, 1/8, and 3/4. Okay? Stat, calc, single variable stats, L1, comma, L2. Okay, so on 1 game, on average, you're going to lose $1, $1.875 negative, okay? So you're doing 2 games. So after 2 games, it's going to be 2 times negative 1.875, which is negative. So on average, after 2 games, you've lost $3.75. Okay? You can expect to lose $3.75 after two games. Not a good game. Okay, 6, skip 6. Okay, we're not doing 6. that's in there. That's a mistake. That's actually from Unit 5. Okay, 7. Okay, here we have a geometric probability. Okay? You got 5 boxes of cereal, and the kid wants, and they got 5 different games, and the kid wants one game in particular. Now we're going to say the probability that the box that has the game that the kid wants is 0.2, 1 out of 5. Okay? So what's the probability that the kid opens 3 boxes of cereal before receiving the desired game? Okay? Well, it's simply going to be 0.8. That's the probability that he doesn't get the box he wants. So the first box doesn't have what he wants. That's 0.8. God bless you. The second box doesn't have what the kid wants. That's 0.8 again. So now we got 0.8 squared. And the third box has the right game. That's 0.2. So it's D, 0.8 times 0.8 times 0.2. It's very simple. Very, very simple. It's not like the probability where you have a fixed number of outcomes, fixed number of trials, and you're looking for a particular number of outcomes. Then you get into multiple possibilities. Okay. Now, here we got, you guys okay? You got any questions? Yeah, okay. Okay, where do the numbers come from? From Numberland. Okay, where do they come from? All right. You have, I just gave this toy to Miss Nolan. It's the thing my granddaughter, anyway, I should bring it in, I'll show it to you guys. This is where numbers come, I'll show you where numbers come from, okay? It's this toy that I got. All right. There's 5 boxes, there's 5 games in 5 different boxes, okay? So what's the probability that a randomly selected box, if there's such a thing, if you could do such a thing, is going to contain the game you want? Let's say you want a particular game. There's games 1 through 5, and the game you want is 3. So what's the probability that you pick the box that has the game you want? That's 0.2. Would you agree? 1 out of 5. Okay? The probability that any randomly selected box does not contain the game you want is 4 out of 5. 0.8. That's where the numbers come from. So the probability of the first box you select doesn't have the game you want is 0.8. Second box, 0.8. Third box, 0.2. So you're looking for the first box that has the game you want. So you can say, well, the first 2 don't have what I want, so it's 0.8 squared, and then the third one has what I want times 0.2. Okay. All right. Okay, 8. 2 independent, continuous random variables. How much water is put in what's the difference between how much water is put in by the 2 manufacturers? One guy puts in 4.5, and the other guy puts in 5.1. So we got can 1 minus can 2. The expected value is 0.6. Okay. So that's, and what's the standard deviation? Sigma of C1 minus C2 will equal the square root of 0.57 squared plus 0.63 squared, and that is 0.85. So it's 0.6 and 0.85. Okay? And we've done this a lot. Okay? The key thing, they told you that there's no reason to assume they're not independent. Right? A can of one thing, a can of another thing. It's hard to think of one can would be affecting the other one. Okay? All right. Home pregnancy tests. Skip. Oh, no. For 9 you can do. Okay? What's the probability if you travel no more than 3 of your next flights will not be on time? This is pretty easy to do. So, the probability that flight's not on time, that none are not on time. None are not on time. We're going down to E here. So the probability that it's not on time is 0.176. Actually, okay? So here's the probability that none are on time. 10, choose 0. And this the binary probability, the formula for it is on your formula is n choose x, p to the x, q to the n minus x. And you have that right here. 0 and 10, 1 and 9, 2 and 8, 3 and 7. So the right answer is E. Okay. Sum of 4 binary probability, yes.
For the last one.
For this one or the one before it?
So if you're doing subtraction, like no matter what, in this, like, no matter.
You always add. Always add the variances.
Even if it's like multiple.
I don't care, look, I don't, even if it's what, I'm sorry, finish your sentence, I cut you off, I apologize. Okay, yeah, but we're not multiplying or dividing these variables. Usually we're just adding or subtracting them, okay? Multiplying or dividing them probably gets in a lot more interesting material, but this is Dick and Jane does statistics, okay? So we're keeping it simple. All right, I'm moving on here. All right, so I'm going to make a tree diagram. So here it comes. We're skipping 10. Okay, we're going to 11 because it's not the material. Okay, so home pregnancy kits. All right, so they say if a woman uses one of these kits, research shows that only woman is pregnant, probably she's pregnant when she uses the kit is 0.3. That she's not pregnant is 0.7. Now, if she is pregnant, it's you get a positive 0.96 and a negative 0.04. And if she's not pregnant, you get a positive of 0.9 and a negative of 0.1. Okay? So, what's the probability a woman is pregnant given in this test? Notice they even use the word given. They're so nice to you. Okay? Nicer than you deserve, probably. Okay, so it's a probability that given that you're pregnant, what's the probability you get a positive? Okay? So that's going to be the probability of positive and you're pregnant divided by the probability of being pregnant. Okay? So, I'm sorry, what's the probability? I gets a positive result. Okay, so positive and pregnant divided by the probability of being pregnant. Okay, so 0.3 times 0.96, that's positive and pregnant, divided by the probability of being pregnant, which is 0.3. So it's 0.96. 96%. Okay? Yeah.
So, the given is that you're
They give here. What's the probability that a woman is pregnant given that the test? Oh, you know what? Yeah. I know I screwed it up. I thought, I had it right on my notes here, and then I'm reading it. I don't know what's my problem. I'm reading it out loud, and I'm second guessing myself. I had it all worked out correctly. You're right, and I was wrong the way I said it, but I have it right on my notes. That's a cold comfort to you guys, but I actually said it to you wrong. All right. So it's the probability of being pregnant given that it's positive. Okay, so that's probability of pregnant and positive over the probability of positive. And that's going to be 0.3 times 0.96 divided by 0.3 times 0.96 plus 0.7 times 0.1. And that's going to be, it's about 80%. Okay? So 20, okay? Plus 0.7 times 0.1. In other words, if you look at the tree diagram, if it's still there, yeah. Okay? So what are the outcomes of no, it's Jesus times 0.9. Yeah, 0.7 times 0.9. Okay, so that's going to be 0.3 times 0.9 0.96 divided by 0.3 times 0.96 plus 0.7 times 0.9. No, it's 0.7 times 0.1.
On the
Point-
top, so you did
Okay,
0.3 times 0.96.
yeah. It's the probability,
That it's positive.
yeah, positive and pregnant. Okay, that's 0.3 times 0.96. Okay, over the probability that you got a positive test, which is going to be 0.3 times 0.96 plus 0.7 times 0.1. Remember, the probability that you're not pregnant and you get a positive test is 0.7 times 0.1. Okay? I still had it. I was right the first time I did it. And let's just be a lesson to you. I don't mean this to be yelling at you guys because it's not your fault. Don't second guess yourself. The first time you go through a problem, that's probably going to be your best shot at it. If you go back and start second guessing yourself, you're going to get messed up. So the answer is 80%. Okay? But does everybody see from the tree? Let me go back to the tree diagram. Okay? Here is not pregnant and positive. 0.7 times 0.1. Right?
That's not permitted. No, it's positive.
No. Yeah, you know what? I put the signs wrong. That's what I screwed up on here. And I had it, Jesus.
It's confusing because positive is
Okay.
positive.
All right.
Yeah.
It's 0.9 and positive is 0.1. Okay? All right, so this is not pregnant and positive 0.7 times 0.1. I'll have to record this all over again next class because I made all these mistakes. And here is pregnant and positive, okay, which is 0.3 times 0.96. So here's the two outcomes where you're pregnant, okay? Sorry about this, all right? When I record this, I'll do it for the last class of the day, and it won't have all these mistakes in it, so you can review it again. But you follow the tree diagram's correct. You take the logic from the tree diagram, okay?
Wait, so what is the answer going to be?
The
Or
answer
what
is,
is the fraction?
it's what?
What's the fraction that you drew?
It's what I have right here. 0.3 times 0.96. The probability that pregnant and positive, 0.3 times 0.96, over the probability that you get a positive result, which is 0.3 times 0.96 plus 0.7 times 0.1. Okay, and that is 80%. Okay, now we're going to skip 12. Skip 12. Is that it? Because there's one more page. Oh, where's my notes? Oh, forget 13. We're not doing 13. We're not doing 12 or 13. I should have that last page on there. Okay. All right. We got through all of this. Okay, this is the review for the multiple choice. Now, you wanted me to finish the problem on the previous packet, so let me do that. Okay, I don't have it with me, but I'll put it up on the screen. I got it in electronic form, so let me get that. Okay, so let's go to the last problem. Okay. Now, what I'm going to do here is you're going to toss a coin 36 times. Great. The first thing I want to do, let's call H is a discrete random variable, describes how many heads you get when you toss a coin a number of times, okay? So we have H. So what's the probability distribution for one coin toss? Okay? So we have H, and the probability of H. Okay? Well, you throw a coin one time. You can get 0 heads, or you can get 1. Now, what's the probability of 0? 0.5. What's the probability of 1? 0.5. Now, it's not hard to see that the expected value of H is 0.5. But what about the standard deviation? Now, I was just feeling unsure. You know, I just didn't want to do the, I actually did this on the calculator. Maybe some of you guys are actually doing it in your heads. So I went to edit, and I cleared this out.
We have to do 0 through 36 for everything.
Hold it, just bear with me for a second. Once you get this, you're all set. So we put in 0 and 1. This is the number of heads you can get. And then the two probabilities, 0.5 and 0.5. Okay? And now I'm going to do stat, calc, one variable stats, second 1, comma, second 2. Okay, so the standard deviation is 0.5, which is what I expected it was going to be. But now we know for one coin toss, okay, now notice the expected number of heads, 0.5, and the standard deviation are the same number, okay? So the expected number for 18H, I'm sorry, for 36H will equal 0.5 times 36 is equal to 18. So we expect 18 heads out of 36 tosses. No mystery there. What's the standard deviation for 36 heads? It's going to equal the square root of 0.5 squared times 36, the number of coin tosses, which is going to equal 0.5 times 6, which is 3. Okay, you guys with me? How I got the standard deviation? Yeah.
Why isn't the 36 squared?
It's, you don't ever square the number of times that you're multiplying the variance by.
Okay.
It's always n, the square root of n times the variance.
It's like before you were just adding every single
Yes,
one.
it's like 0.5.
0.5 squared plus 0.5
It's like 0.5 squared plus
36
0.5
times.
squared
Because
plus,
that's how we usually do it. It doesn't change it times 36.
because it's the same number. Thanks, Ed. Okay, so it's 36 times 0.5 squared, which is going to be 6 times 0.5, which is 3. Okay, so we got the mean and standard deviation of, so it's 18, comma 3 for 36H. Okay? Now, if the coin were tossed, how many extra heads are observed if you go in 2 standard deviations? Well, we're going to draw a normal curve. 18 is the expected number. The standard deviation is 3, right? So here's 21 and then 24. So 2 standard deviations is 24 heads or more. So an unusual number of heads would be 24. Or conversely, an unusual number would be 12, right? An unusually small number. An usually large number of heads would, if you're calling that 2 standard deviations. Okay? You guys with me? Now, the ratio, the mean divided by standard deviation for 1 was 0.5 divided by 0.5, which was 1. Now, what's the ratio of the mean to the standard deviation now? It's 18 to 3. Let's do it the other way. Let's do standard deviation to mean. The ratio of the standard deviation to the mean is going to equal 3 over 18, which is 1 over 6, right? So the ratio went from 1 to 1 over 6. Okay? So the ratio, in other words, the ratio of the variance got smaller. The output got more normal. Okay? Now, what about for 100 heads? So, what's the expected outcome for 100 H's? What's that going to be? Expected output for 100 H's. 50, okay? Now what about the standard deviation? Standard deviation for 100 H's is going to equal the square root of 100 times 0.5 squared. And what is that? 100 times 0.5 squared, what is that? 5. It's going to equal 10 times 0.5, which is 5. Okay, so what would be an unusual number of heads? Well, we got 50, 55, 60. So 60 would be an unusual number of heads. Okay? Now, what is the ratio of sigma to mu? 5 over 50. It's now 1 over 10. It went from 1 to 1 over 6 to 1 over 10. Okay, the ratio is getting smaller. All right? So, the last question that you have to answer is, explain how these results refute the law of averages. Let's talk about how they confirm the law of large numbers. That's the one I want you to talk about. How do these results confirm the law of large numbers? And let's start out, somebody tell us the law of large numbers. You can look it up in your book, but it's a good thing to know. What is the law of large numbers? Can anybody explain it in their own words without looking it up? Because it's really just common sense. Michelle, let's hear it.
Isn't it just, I'm not for sure, but isn't it just that, like, even if the numbers that you're calculating get bigger, they'll never approach zero? Or is that,
What will never approach zero? Okay, well, you're off to a really good start in that you're talking about the number of trials increasing. Okay? That is a huge part of the law of large numbers. Okay? Nico.
Isn't it that the more trials we have, the closer it's going to be?
Closer, what is to the
The results that we get.
the results that we get? Well, the results that you get have a mean. So, I mean, they have a specific, they have an experimental mean. Okay? But what does that mean approach as the number of trials increases? What was what you expected half a head if you tossed the coin once with a standard deviation of 0.5, right? Okay? You could get 0 or you could get 1, right? Okay. If you got a 0, you got none. If you got 1, so either your choices were between 0 and 100%, right? Okay. Now, what's the theoretical mean is 0.5. Okay, so your actual results can't ever come close to that, right? If you throw the coin one time, right? You're either going to get 1 head or none. You either get 100% heads or no heads, right? Okay. So, but the mean that you calculated based on your probability model was 0.5. What happens as you throw the heads as you do more and more trials? Maddie.
Standard deviation will be smaller, so.
Well, no, it's not getting smaller. Standard deviation is getting bigger, right? Started out as
Well, I mean
point.
bigger, so this, like the z-score of the actuals will be smaller.
The z-score of the what?
But like,
No, you guys are getting too technical. You were really close to the answer. You're very, very close to it. Okay? All right. Here's what it is, okay? And this is something that you already know. And you've really kind of put the pieces out. But let's see if you can write this down, okay? And let's put this down. Alex, somebody poke Alex there. Wake her up. Okay? All right. As the number of trials the number of trials increases, the experimental results, we're calling this experimental because it's something you're really doing, okay, if you're really flipping a coin, or even using a number generator, the experimental results get closer to the theoretical result. Theoretical, in parenthesis, mathematical result. Okay, so the more trials you do, the closer that your experimental mean. Okay, if you do you do one trial. Okay, what's your experimental mean going to be? It's going to be 0 or 1, right? It's going to be 0 or 1. You do 2. What can happen? Okay, you do flip a coin twice. You can get 2 heads. You can get 1 head. Okay, no heads. The more times you flip it, the closer that your actual number of heads approaches your expected number of heads. Okay, that's number 1. Okay, and along with that is the variation in the results decreases. Relative to the number of trials. Okay, now nobody was able to tell me this. Okay, so make sure everybody's got this written down. Okay, this is the law of large numbers. As the number of trials increases, the experimental results get closer to the theoretical, that is the mathematical result. The variation in the results decreases relative to the number of trials. Okay, so the ratio of standard deviation to the mean will decrease as the number of trials increases. Okay, so this supports the law of large numbers. Yes, Maddie.
In part B, are they saying that having 2 standard deviations above the mean is unusual just
Yeah.
in this case, or always unusual?
It depends. It's often used as a definition of being unusual. Although,
So,
depending on what your standard is of what you accept, you got to go way beyond. I mean, 2 standard deviations is considered to be a gross, area for error or whatever, or it's not considered to be unusual. 5, 6, 7 depends on, depends on how you're using it or whatever. But in general, for the sake of this course, it's unusual.
so would D be 10 then?
Yeah. Well, no, not 10.
10 then, because the standard deviation is 5.
60. 50's in the middle. I drew the picture.
Oh, 10 extra heads then. Wouldn't it be 10 extra heads? Yeah.
Yeah. So 60 or more is unusual. All right. Anything about the multiple choice questions? All right, I'm going to stop the recording. But like I said, I'll probably have to do it over